All right. This week we're going to start talking about atmospheric pressure. So we've learned about energy coming into the atmosphere this past week. And then we learned about the fact that temperatures and what they do. And what that means is basically molecules, how they vibrate, and that is a temperature. So now we're going to take another, why do meteorologists care about pressure? What's significant about it? So we're going to explore that. And we got to understand what it is really. So what is a pressure? It's a force. Every object applies a force to something. It's the mass of that object times an acceleration. So if your car hits something, your car has weight or mass, and it's moving, it has an acceleration, and when it stops, it has a big acceleration downward. That generates a force. Well, air molecules do the same thing. Air molecules move because they collide with other molecules and they generate a force. Total air pressure is the cumulative force of all these collisions. And guess what? Depending on what gas is mixed together or whatever, each gas is a separate amount of molecules. The total of all the gases in the atmosphere, each individual pressure, will make up the total air pressure for the atmosphere. So, and it depends a lot on the motion of the molecules and how many of them are in a given area, how they're packed together. So the lower part of the atmosphere is where gravity has pulled a lot of these molecules down. And air is something that is compressible. So if you think about water, if you try to squish it with your hands, you really can't squish it. But if you do try to squish air, it actually does compress in your hands a little bit. So that is what one of the big differences between water is considered a fluid and air is actually considered a fluid when we're dealing with things. But their difference is water is incompressible and air is compressible. So how do we measure air pressure? Well, the old days, we used mercury barometers. But mercury is kind of a dangerous substance, we learned with time, unfortunately. It took some problems to discover that. So we tend to shy away from mercury barometers now. But the original idea with the mercury barometer was you took all the air out of a tube, sucked it out, and then stuck it in mercury, a pool of mercury. And the air would push the mercury up that tube. And that how high up it went was the weight of the air. So the idea was that you could actually measure the weight of the air that way. And typical air pressure, supports mercury at about 29, almost 30 inches of mercury. So with that, here are some tables, just a quick glance at looking at different ways of looking at pressure. Most of you are going to be familiar with an inch of mercury, so you're going to hear things on the news like 30.15 inches of mercury or 29.95 inches of mercury. The reason they give you inches of mercury is that we like English units in the United States, and we tend to also, everybody's used to a barometer at home. Most of them read in inches of mercury. So the newscaster isn't going to try to confuse you. He wants you to have it easy. So he's going to stay with inches of mercury. I, on the other hand, and meteorologists like to deal with millibars. Why? First off, it's much more easy to calculate equations, and it's a pretty good representation. 1,000 millibars is approximately around the surface of the Earth. So now that we know this, a little bit about the different types of measurements, air is compressible and the drop in pressure with altitude is greater in the lower troposphere. So in other words, more and more of the air is compressed in the first few thousand feet. The higher up, the further the air molecules get apart, and the pressure doesn't drop as fast. So And they've actually looked over time and over seasons and developed an average for what they would call the standard atmosphere. It's a way to just measure what you would expect the temperature to change with height, how you would pressure to change with height. One of the interesting things is here's a depiction of how the horizontal air pressure changed. You had a low pressure going by here. The lowest pressure was between 19 and 22 local time. It was around 1,008, a little bit under 1,008, maybe 1,007 millibars. So you had low pressure that moved in, and then high pressure followed it as the low pressure went out. So you can see the pressure rose. One of the things I want you to notice is look how little this pressure change is. The maximum here was 1020. The minimum was 1,008. That's 12 millibars of pressure change. If you went into vertical and you wanted to know where 850 millibars was, for example, it's roughly 5,000 feet up. That's a pressure drop of 150 millibars in 5,000 feet. Here on the surface, however, you see we only had a 12 millibar pressure drop. So pressure changes a lot slower in the horizontal than it does in the vertical. The rising air temperature will increase the average kinetic molecular activity. So if I applied heat to air, the molecules are going to start shaking harder and harder and faster, and they're going to tend to expand apart. Remember, the atmosphere doesn't have a big glass dome over it holding the air in. So what happens is the faster they go apart, they tend to spread out. So they're going to be less molecules in any one area compared to what's in another area where the atmosphere is much colder. The molecules are going to come closer together. There's going to be more mass. So the atmosphere is actually going to weigh more where the temperatures are colder, typically, than where the temperatures are warmer. So air pressure will definitely drop much quicker in vertical when you have cold air and it's dense. So that's why we talk about the tropopause being higher at the equator. Well, those air molecules pushed it up. They moved apart. It's much warmer down there. So the 500 millibar surface is about halfway below in the atmosphere. So it'll be at a lower altitude when the air is typically colder. So we had some really cold air this past winter come into parts of Texas and all. If you were to look at the 500 millibar charts, they would show a big trough of low pressure aloft. However, at the surface, remember, very cold air is very dense air, so the surface actually had high pressure. So you had high pressure at the surface, but because the air is very cold, you have low pressure above it. Kind of confusing, isn't it? One of the things about knowing about air pressure is convergence and divergence. Well, air converges, it's pushing the air together, so you have more molecules there. You're going to tend to have a higher pressure. It's going to push, but remember, all air moves, so it's going to push it down if that high convergence occurs aloft, and that would spread it out at the bottom, causing divergence. And this would push the air down to sink, and this would be a high pressure system. If you had the other way, you had divergence aloft, air coming in at the bottom and rising up, you're going to get low pressure at the surface. You wind up with the other way, a low pressure system. So one of the things also here in the ideal gas law, which we're going to talk about, there are three variables that can change: density, temperature, and pressure. So if I know what pressure and temperature are, I can figure out density. If I know what density and temperature are, I can figure out pressure. So as long as I know two out of the three variables, I can always calculate the other variable. So one of the interesting things is at a fixed pressure, temperature is inversely proportional to density. So another thing with the atmosphere is there's something called expansional cooling. when the molecules are pulling apart, they're actually doing work, pushing outward away from each other. That causes the energy to dissipate in the air, and it cools it. Say you release air from your tire, you feel the cold air coming out. But on the other hand, if you pump air in, man, it gets really hot. Some of the cylinders of the pump, I know I've touched some and almost burned my hand at times where I've been pumping. So that means that as air rises, it's going to go cooler, and as it's ascending, it's going to get downdraft and get warmer because of this expansional cooling and compressional heating. And here you can actually see a diagram of that. So what does that mean? It means that you can actually calculate what should be a temperature that the atmosphere will drop at as a parcel of air rises. That parcel of air, and I'm going to talk about parcel of air a lot, can be any size. Just for an example, 500 feet by 500 feet, 1,000 by 1,000. As that air rises up, it's going to cool 9.8 degrees Celsius per 1,000 meters, or roughly 5.5 degrees Fahrenheit per 1,000 feet. So if you climb up a mountain and go up, say, 3,000 feet, you're actually going to be on a normal conditions about 16 degrees colder than it would be at the surface down by the bottom of the mountain. And that is a dry air parcel. We're not talking about any moisture, no water vapor worried about in this air parcel. However, when water vapor comes in, that changes things. And we'll talk more about that next week. But right now, just say that moist adiabatic lapse rate is only about 6 degrees per 1,000 feet. So it doesn't cool as fast. So with that, I wanted to show you a couple things here. Just quickly. Here's the surface weather map. Look at the pressure. Here is the pressure at 994 millibars. High pressure over here at 1028 millibars. In the horizontal, the pressure isn't changing that great. Yes, this is a major low, bringing really bad weather to this part of the area. This is a nice high pressure system. And notice how cold the air is at the surface. But if you were to look aloft, you have a trough of low pressure. Again, following what we just learned, that in cold air, pressure drops much quicker in the vertical. So you wind up with, at the surface, cold high, aloft, cold low. One of the other interesting things here with, this is a sounding. It's a vertical sounding. And what we've done here to make this a little bit easier for meteorologists to look at is we've compressed the pressures closer together at the lower levels and further apart at the upper levels, which is what really happens in the atmosphere. And you can actually see here temperatures cooling with height, a little bit of warming here. One of the things I wanted you to notice was that while we said 9.8 degrees was the average, or what it could do, almost always the atmosphere does not cool that fast. And a matter of fact, it never cools faster than that. So you wind up with an air parcel that if it was cooling at 9.8 would almost always be colder than the surrounding air. So something to think about. Hope you got a little bit out of this pressure. And if you have any questions about pressure, please don't hesitate to ask.